Good morning. We are reaching towards the end of the course. So today is second last lecture. The Monday's lecture we will conclude the course. So today we will be learning a more advanced topic. We will not be really learning, but getting exposed to a topic what is called as a metal plasticity. So till now we have been dealing with all the materials which are elastic. That provides a lot of advantage in doing calculations, but there are some situations where the dealing with material plasticity or plastic phase of the material behavior is very, very essential. So what is plasticity? You are aware of. So if you plot a stress strain diagram, you will find that till some time the stress strain relationship is linear, and after this point you find that the stress strain relationship it becomes non-linear. So this much zone is called as the elastic zone, and when material goes beyond what is we call as the yield strength, it is called as a plastic zone, or the behavior of the material is plastic. So today we learn if the material goes in the plastic zone, what are the theories or what are the principles based on which the behavior of the material or the design of the components it can be done. So before that, let's understand which situation demand this particular theory. So can you think of some applications where working in elastic zone is not useful? You must work in the plastic zone. So you cannot operate there when the stresses are below elastic limit. Necessarily you have to cross the yield limit and go in plastic zone. Can you think of any applications where you must make the material to go in plastic zone, that is beyond the elastic limit? So that is not the choice of engineer, it is the need of the application that it must go in the plastic zone. Railway tracks in what sense?
Like skin hardening helps you maintain the excess pressure that the railway can have. Like, so if change in load increases, that track should sustain that amount of power.
Okay, so what we are talking about is what is known as work hardening. That is, you make the material to go beyond the yield strength or go in the plastic zone in order to enhance its strength. We'll touch upon that. Okay, so that is one particular aspect. So that is work hardening or strain hardening. Yeah, that's right. So that is where one would use going in plastic zone. Which are the other applications where you must go in the plastic zone? So one characteristic of plastic zone is whenever you go in the plastic zone, the material cannot come back to its original shape. It remains permanently deformed. So can you think of some applications where you want permanent deformation by the application, need of the application? Where we don't want the material to come back after loading to its original position, we want it to become permanently deformed. So what are the applications where this is required? So you can think of many manufacturing processes which require this, which already you are studying now. Any manufacturing operation which involves drawing, so that will involve reduction in the diameter of the wire. If you are talking about wire drawing, so various types of drawing operations. What else? So I learned many manufacturing processes. Hammering. So hammering is not the name of the process. Okay. So that is a tool. So you can call a forging process or bending process. So that would be another process. So bending or forming. So these are the applications where a rolling operation, you are making some cylindrical pipes by taking flat plate and rolling it. So those are the applications where you must deform the material beyond the plastic zone. So this type of applications, they are called as high strain plasticity. High strain metal plasticity, where you are operating somewhere far away from very large amount of strength you are restricting. So you are not only crossing the yield zone, but you are going much beyond that so that the material remains permanently deformed at a large amount of deformation. So it is not few microns elongation that you want few millimeters of elongation. So that is called as high strain plasticity. So these applications definitely need to know what happens to the material, or how do you ensure that when the material is bent, it will not crack or it will not break. So that calculations will require the knowledge of or the theory of metal plasticity. Another applications, they are called as low strain plasticity. They are typically used for optimum design of components where, for example, aerospace industry or marine industry, where weight is very important application. So you want to minimize the weight as much as possible by making the component thickness, for example, smaller and smaller. So there is a limit. If you restrict yourself up to yield strength, then there is a limit up to which you can reduce the thickness, beyond which you cannot do. But if you want to reduce further, you have to go little beyond the yield strength, not as much as what we do here. So you cross the yield strength by a short amount, and you get a considerable advantage in terms of the size. So these are mainly the applications are aerospace or marine applications. And this particular low strain plasticity is also very much linked to what is called as a fatigue design. So in the fatigue design, the application of low cycle or the low value of the strains, there is a separate theory which is useful for optimal design of this particular set of components. So that is the background or the motivation why we need to understand this theory of plasticity. Now we'll also understand some characteristics of plasticity. One thing is, as we said, that it is irreversible process. So once the material deforms, it is permanent. You cannot get it back to the original shape. So that is advantage and disadvantage in some applications. The second thing is it involves dissipation of energy. So I don't know whether your batch has done physical tensile test. Your batch did in the laboratory tensile test, or you did virtual? Okay. So immediately after the tensile test, if you touch the specimen, you will find that the specimen has become hot, because while doing this plastic deformation, lot of internal structures or metallurgical structures, there is some internal friction which has to be overcome, and lot of work is being done internally. So that some part of that it gets released in terms of heat. So that is why fine temperature rise. So it involves dissipation of energy. So not all the work done while deformation gets stored as a plastic work, but part of that it gets dissipated as a heat energy. So that is another aspect. And the one more characteristic of the low strain plasticity, or not low strain plasticity, but the plastic analysis, is that during this operation, the material deforms permanently, like the same as the first point. And you cannot get it back. This particular permanent deformation is explained in terms of the metallurgical processes, what material science you are learning. So there are dislocation theory or dislocation moment theory, which explains why the material behaves the way it behaves. Certain materials behave in the manner in which it is shown here. So if you want to know the physics behind how the material plasticity operates, one has to take help of the material science approach, where you will be learning how the internal grain structure or the crystal structure deforms, and which leads to dislocation movement, and the permanent deformation happens because of that. So that is the background about the plasticity process. Now we'll understand some of the terms and some of the phenomena which are associated with metal plasticity. Let's consider a case where you are loading a material from no load state to up to the yield point. Let's call this point as A. So when you are moving from point O, zero load, to the load at which the material starts yielding, O to A, and at that time you start unloading, you will find that the stress strain curve follows exactly the same point. So if you are going upward from O to A, while coming back, the material will, or if you do the testing, you will find that the stress strain curve will have exactly the same point. So within the elastic limit, there is no change in this particular loading and unloading path. Whereas if you go in the plastic zone, so let's say you load it beyond the yield strength, you reach point B. Okay, so at this point, let's discuss. So at this point, from point B, if you start unloading, I'm giving you three choices. You can tell me what will happen. One is that from B, this is choice number 1. The choice number 2 is comes down in this particular fashion, and choice number 3 is somewhere in between. So what do you think will happen if you take a rod, cross it beyond the yield strength like you did in the tensile test, but if you don't stretch it till the tensile strength, ultimate tensile strength, but you start unloading it before that. So you have loaded it up to some beyond yield strength and you unload it. So will it follow path 1, part 2 or part 3? So what is your guess? Or what does your intuition say? Second part, that's right. So the material doesn't go back to this particular state. Why it happens, we will see. But there is one more interesting thing to be noticed here, is that when you are unloading it from the yielded state, an interesting point to note is that it follows a path. As I said, it doesn't go to origin or it doesn't come down directly vertically down, but it follows a path which is parallel to the original path. So if this particular line, it has got slope which is the Young's modulus E, while unloading, the unloading path will also exactly take the same Young's modulus. So the slope of this line will be equal to slope of this line. So both the lines are parallel to each other. So that is the interesting thing that is to be known. So the material as such remembers that even if it has yielded, it doesn't let go of its basic property, that is the yields, that is the modulus of elasticity. it still follows the same line, and these two lines are parallel. Okay, so let's say we have come to point C, which is at which stage the stress has become 0. So as you can note here, when you have come from B to C, the stress has become 0. That means there is no more load acting on the specimen, but there is a strain which is existing at this particular point. So from O to C, which is on the strain axis, so there is some strain which we call as a permanent deformation in this material. So after loading and unloading, the material has got some permanent strain. So that is called as a plastic strain, denoted by epsilon P. So this component is called plastic strain. It started with point B. So in the point B, the total strain is epsilon. So originally it was strained to point B, which if you call the strain is epsilon. After it is fully unloaded, part of the strain it gets recovered. So this much part of the strain is recovered. So that is called an elastic strain. And the remaining part, it is not recovered. So it remains, the material remains elongated, corresponding to strain equal to epsilon P. So if you multiply epsilon P by the length of the rod, you will get the permanent deformation of that particular rod. And whereas the epsilon E is the component which gets recovered as you unload from any yielded component. So if you go beyond yield point and unload it, some part of the deformation you will recover. So that is called as the elastic strain, and another part is not recovered. So that is called as a plastic strain. So the total strain consists of two components. One is the plastic strain and another is the elastic strain. And usually the range, if you draw this stress strain diagram to scale, so for steel, if you draw the stress strain diagram in actual 2 scale, you will find that it will have behavior something like this. So if you are in large strain point, so if you are somewhere here and if you recover back, you will find that the elastic recovery or the elastic strain is much smaller as compared to the plastic strain. So usually in the plastic analysis, one ignores the elastic strain component and considers only the plastic strain when you are doing large strain plasticity. So that is one point to be noted. Another important point which we discussed about that railway track hardening. So that particular phenomena is called as a work hardening. So what happens from C is another interesting. That means you have taken a rod, you have stretched it beyond the yield point, unloaded it, so it remains elongated. And if you start again loading it further, that is again you start another load cycle, you will get an interesting observation. So from point C, if you start loading this component, you will find that it will again follow the same path. Now this is your yield point. So what you expect is that is the common sense we think that it will go up to the yield point and then it will start deforming. So this is what we expect. However, the real material has got, or the materials that we are discussing, the steel and other regular engineering materials, they as if remember from which point they have been unloaded. So they reach right up to the original point B, and then they will start going plastic deformation. So it is as such the yield point which was originally sigma y, because of the one load and unload cycle, it got enhanced. So this particular mu sigma y dash is greater than the original sigma y. So material which was never loaded, once it is undergone one load cycle beyond the yield strength, you will find that in the subsequent cycles its yield strength will be enhanced. So this particular effect is called as strain hardening or work hardening. So this, the definition or the process of strain hardening is that you take a component, load it beyond yield point, and again bring it back to zero load condition. In the next cycle of loading, you will find that because it has gone beyond the yield strength, its yield strength would have increased. And since the design calculations, we use the yield strength as a basic property. If you want to use higher yield strength, so suppose you order some material, it comes with 250 MPa, but for your design calculation, you require 275 MPa. So one trick that one can do is just, if it is possible, then uniformly stretch that material beyond the yield point, where it's stretched beyond 250 MPa up to 275 MPa, unload it, and then when the next time you load it, you will find that till 275 MPa, it will not yield at all. So it will behave elastically till the higher value of the yield point. So this is a very useful trick or the solution for many problems that where you want to quickly increase the yield strength. However, for the most common, some of the materials, which includes steel, which is very popular material for us engineers, mechanical engineers, there is something odd thing which happens when you undergo strain hardening. So that effect is called as Washington effect. Have you studied this in your material science? Work hardening, at least you must have been exposed either in material science or manufacturing. Have you heard this term, strain hardening or work hardening? Okay, so which course?
So,
Okay, strength of material. Okay, okay, that is okay. So that is another subject where you can learn this. So this is called as a work hardening. But this work hardening or strain hardening, which is advantageous, but it comes at some price, and that is explained by what is, or that is considered as what is called as a Washington effect. I don't think Washington effect you might have come across earlier. Okay, so what Washington effect decides? So this is not applicable for all materials, but only for certain materials. Which includes steel. So in this case, the Washington effect shows what price you are paying for increasing the strength by doing the work hardening. So if you consider a material, so this is strain axis and this is the stress axis, and I am considering the material to have same yield strength in tension and in compression. So let me call it as sigma yc and sigma yt. So that means if I load the material within the elastic limit between sigma yt and sigma yc, it will follow a straight line, which is the elastic behavior of the material. But if I go beyond the yield strength, so if I load it beyond this particular point and then unload, that is what we have seen, it will follow this particular path where it comes to zero stress, and from here onward again you start loading it, you will find that the yield strength would have increased. So that is the strain hardening effect that we have seen. But what happens if you cycle it not in the tensile direction but in the compression direction is something which is interesting to observe. If you start loading the component which has undergone one tensile cycle to a new compression cycle, what happens is this material, what you expect is that this particular path should have come up to the yield strength, or considering the strain hardening, you may imagine that it may go beyond this point and then it will yield. So that is what is the expectation. But it is observed that for many engineering materials with an increase in tensile yield strength, there is a corresponding decrease in the compressive yield strength. So this particular material, if you are loading it in negative direction, you will find that its yield strength in compression, it doesn't remain same, it doesn't increase, but in fact it decreases. So it will start yielding. So sigma yc dash is smaller than sigma yc, where sigma yc dash is the compressive yield strength which you have obtained after the material has undergone work hardening in tensile direction. This particular effect, where the increase in elastic limit in tension direction causes decrease in the yield or the elastic limit in the compression direction, is called as the Washinger effect. So Washinger effect essentially means that if you have increased the elastic limit in tension direction, you pay the price in terms of decreasing the yield strength in the compressive or the negative direction. And the reverse also remains true. If you strain harder in the compressive direction, so you first load the component in the compressive direction beyond yield point, you will find that its compressive yield strength will increase, but the tensile yield strength, because of Washinger effect, it will decrease. So there are theories to explain why it happens for certain materials, but that is beyond the scope of this particular course. But this point is to be remembered is that as long as you are using work hardening to increase the strength of the material and you are remaining in the tension zone, so you are never going to go in compression, this is beneficial. But if you are going in tension compression type of application where the component is undergoing both tension and compression, so for example you have a plate which undergoes bending in one direction, bending in another direction, so the top fiber will undergo compression one side, and that is tension one side and compression other side, the top surface. So in such case, the Washinger effect comes in picture, where in one cycle, on the tension cycle, you will get higher yield strength, but on the other cycle, you have to consider the decrease in the yield strength of the material. So that is the point to be noted. So any question till this point? Have you understood what is Washinger effect? So can somebody tell in just simple words what is Washinger effect? So starting, if you load in tensile direction beyond yield strength, the elastic limit in yield strength increases. That is the one part. Load in tensile direction beyond yield, it increases tensile elastic limit. So this is the first part of the Washinger effect definition. Can you complete the second part? If you load in tension, its elastic limit in the tensile direction increases. However, what will be the next sentence? Its subsequent elastic limit in the compression direction decreases. So after this, if you go in the compression direction, it decreases. Or if it is initially compressive, then the tensile will decrease. So that is the Washinger effect. Okay, any question till this point? Okay, so all this particular material plasticity, it depends on the definition of yield strength. So we have obtained this stress strain diagram based on a tensile specimen which is uniaxially loaded. So it is easier to predict when the yield of that particular material will happen. But in real life, you don't deal with only bars and beams which are uniaxially loaded. You have more complicated loading which are going to happen. So in actual case, you will have some component which is loaded in more complex conditions. So you have some component which is subjected to axial load, subjected to bending moment about 2 axes, and it is subjected to torsion as well. For example, so in this case, at any point of this particular body, you will have the stress state which is defined by the stress tensor. So we will have the 6 stress components. So we will have sigma x, sigma y, sigma z, tau xy, tau yz, and tau xz. So that is the stress state at this particular point. Now, how do you define whether this point is going to yield or it is not going to yield? So that is the question that we have to solve. So do you remember any solution that we use for this situation? So we want to decide whether this point the material is going to yield or it is not going to yield. So can you say that it's sigma x or sigma y or and so on? If any of them increases beyond yield, then the material yields. So can this be acceptable theory? So it is difficult to say only based on the magnitude of individual stress component whether the yielding will happen because of this or not. So we use another approach. So we convert this stress components into another numbers which we use for our comparison purpose. So we talked about some theories of failure. So which we have learned only a single theory of failure. So which is that theory of failure? So in the pressure cylinders, for the failure we use the maximum principal stress theory. So which we convert from these components, we can calculate the three principal stresses. And as per the maximum principal stress theory, the maximum of sigma 1 or sigma 2 or sigma 3, when it exceeds the allowable, then the material fails. That is what we are talking here. So instead of allowable, if we use here some component which corresponds to the yield strength, if we say that if any of these principal stresses it exceeds the yield strength, then the material will yield. So that is a hypothesis. I am not saying that is the correct thing to say, but as per this maximum principal stress criteria, the prediction of yield strength at this point would be done if the principal highest, the maximum principal stress at this point is crossing yield strength, then this point will be considered as yielded. So such hypothesis or such criteria, they are called as yield criteria. There are multiple yield criteria. That means for different material, different yield criteria are prescribed. The simplest, and for each failure theory, there is a corresponding yield criteria. So the first theory, that is the simplest one, is the maximum principal stress theory. Of the ranking theory. We say that the yield will happen when maximum of sigma 1 or sigma 2 or sigma 3 exceeds the yield strength. So this approach, the left hand side, is called as yield function. So when you are dealing with metal plasticity, you will find that there are different yield criteria, and corresponding to each criteria there will be different yield function. So in general, in order to determine whether you have to consider the material as gone in plastic zone. So that is the first premise based on which the further theories will be established. So first we have to decide whether this point has undergone yielding. So how to decide that? So there are different criteria. One of the criteria could be maximum principal stress theory. So in this criteria you will calculate whichever is the maximum principal stress. If it has exceeded yield strength, then we will call that this particular point has yielded, and then you apply the further theories. Those are there in plasticity. So the first step in plastic analysis is to establish whether which region of your component has undergone crossed the elastic limit and has entered into plastic limit. So if I apply some load on this table, so how much region of this table has undergone in plastic deformation can be established from calculating the contour of the maximum shear stress. So which zone has maximum shear stress beyond yield strength, so that much zone we call as gone in plastic zone. So in general, this can be written as a function of sigma 1, sigma 2, sigma 3. And there are other components which for the simplicity we will not consider, which includes the effect of work hardening and other things which we'll ignore at this particular point. So this equal to C, where the C is some material component or material constant. So this is called as a yield criteria in general. So for example, max of sigma 1, sigma 2, sigma 3 is one of the yield function. When it becomes sigma y, where C has taken the sigma y, we will say that the material has yielded. So that is one of the criteria. The second common failure theory is maximum shear stress theory. It is also called as the Tresca theory. So in this particular theory, the function is maximum of sigma 1 minus sigma 2 by 2 . So as per this particular theory, the yielding is said to be happened when the absolute difference between any two pair of the principal stresses, that is sigma 1 minus sigma 2 by 2 and mod of that, that is the unsigned value. So whichever is maximum when it crosses yield by 2, so that is called as the Tresca yield criteria. So the corresponding theory is the Tresca failure theory, in which instead of yield strength you can put the allowable stress. So that is the Tresca failure theory. What we are looking here is Tresca yield criterion. So as per Tresca yield criterion, whenever this condition is met, the material is supposed to have undergone yielding. So the initiation of the yielding is shown here. So there are multiple, if you open any finite element software, for example ANSYS, you will find that there are different material models are being presented to you, and in that model you have to choose the yield criteria. So there are Tresca criteria, there will be von Mises criteria, there will be Drucker-Prager criteria and so on. So there will be for different material, different yield criteria will be there. So knowledge of this would be required if before you do plastic analysis, which material model or which yield criteria to be selected is required. So this will give you some at least exposure to what yield criteria is, so that when you read documentation you can make out what is the meaning of the material model which you are going to select. Now based on this yield criterion, there are some, whenever you are doing the analysis using this yield criteria, one generally doesn't use the actual stress strain curve. So for calculation purpose you will have to use the stress strain curve. So one aspect of plasticity is how do you decide the material whether it has undergone plasticity or no. So that is the yield criteria. The other is once the material has yielded, in order to do the analysis you have to use some model which tells you how the material behaves after the yield strength. The accurate way of doing that is you provide actual stress strain data and the material will behave as per this particular condition. So that is the actual material model. However, when one uses this particular approach, you have to supply the data of the material stress strain curve to your numerical method, maybe finite element method or any other model or any other method, mathematical model that you are using. It becomes computationally very expensive to use the actual stress strain data. So some simplification is done one common simplification that is done for the preliminary analysis is called as elastic perfectly plastic model. So in this model, up to elastic limit, whatever is the yield strength, you consider the actual stress strain curve, and beyond that, you consider not this hardening effect, but you consider the material to remain straight, or it simply flows beyond the yield strength. The stress can never exceed the yield strength. So this is called as linear elastic perfectly plastic model. Which is commonly used for the first iteration, or just to understand how the material, how that component is going to respond to the beyond yield load. This particular criteria would be used. For more accurate estimation, one uses what is called as bilinear model. So here, up to the yield point, the behavior is same, but after this, one considers another straight line, which is having slope, which is maybe average of whatever behavior other years. So that is called as a bilinear model. And there are other models which are including some exponential curve beyond the yield point and so on. So we'll here restrict the discussion only up to these two models. So these are the two models which are used for approximating. So the purpose of this model is to approximate the stress strain behavior to reduce the computational load. So with now the computational power increasing so exponentially or so fast, the use of this model seems to be not so relevant. But however, for the quick guess, even for the most powerful computer today to do a proper plastic analysis, for example, a car crash analysis, one requires several hours in order to run that particular analysis if you use the actual stress strain model. In such case, to get a first feel of what is going to happen, one usually adopts the elastic perfectly plastic model. So this allows you to do the calculations in a much simpler manner, and also using this model one can develop analytical, that is the equation based approach, which is not possible for data driven models such as the actual experimental data. Okay, so that is another subcomponent of plastic analysis. So whenever one is designing the plastic analysis, it is almost always one adopt to some kind of numerical method, and there one has to use the stress strain model, which is defined as given here. In order to define what is the sigma y, you require a criteria which is as given here. Okay, so that is about the stress strain model, and we'll look into what is called as the visual representation of these models. So there is a typical representation in which the different models are graphically represented so that you can compare the behavior of the material in different situations. The representation is done in terms of if you want to represent how the yielding happens, one would consider a three-dimensional space where the three axes corresponds to the three principal axes. So sigma 1, sigma 2, sigma 3 are the three principal directions along which you orient your coordinate system. And then you say that a point in space, so this particular component, let's say, has value sigma 1 star, sigma 2 star, and sigma 3 star. And we know that based on one of the yield criteria, this particular point lies on the yield surface. Yield surface in the sense it meets the criteria perfectly. So this function, the yield function corresponds to this, equals to yield strength or whatever material constant that we are considering. If we join all such points together, where the failure or the yielding is going to occur, you will get a sort of a surface. So this is some kind of surface one would get, where all points on this surface represents that the yielding is going to happen. So yield criteria is met. If we join all such points, you will get a surface. This particular surface is called as the yield surface. However, it is difficult to represent this in 3 dimensions, or to, in the book form or paper form, it is difficult to project or visualize this surface always in the 3-dimensional form. So one uses what is called as graphical representation on what is called as deviatory plane. So this is a plane in sigma 1, sigma 2, sigma 3 coordinate system. So in the same space where the sigma 1 is aligned about the first principal stress, second and third, this particular plane has got, if I call this particular plane, it has got a normal. So if I draw normal to this plane, it has got direction cosine as 1 by root 3, 1 by root 3, and 1 by root 3. In the initial analysis, we had done some numerical problem considering a plane. So this is a plane which is equally inclined to all the 3 axes. So that means this particular plane is equally inclined to sigma 1 axis, sigma 2 axis, and sigma 3 axis. And the yield surface, which is in 3 dimensions in sigma space, is projected onto this plane. So you can imagine that somebody is looking from this direction, normal to this particular plane. One would observe the axis as, so these are the 3 axes, sigma 1, sigma 2, sigma 3. The deviatory plane is having a vector which is equally inclined to sigma 1, sigma 2 and sigma 3. So the space angle is same. And if you look from this angle, you will find that these 3 axes, they will appear in the isometric fashion as inclined to each other by 120 degrees each. And the surface, yield surface, which is shown here, you will find that the yield surface has got an axis which is always along the inward direction. So for example, one of the criteria is the von Mises criteria, where the yield surface will look as a ellipse in this particular form. This particular curve is called as yield locus. And the surface, if you project this surface in 3 dimensions, that is called as the yield surface, which we already discussed at this particular point. So these topics are just for you to get exposure to what things are involved. So these are not required for calculation, that is for comparison between the 2 theories. What happens? One would have to compare, let's say, the Tresca criteria and some other criteria, von Mises criteria. So one can visualize them better on the representation on the flat surface, and the chosen flat surface is called as deviatory plane, or in the textbook you will also call it is being called as a pi plane. So pi plane is a plane which is equally inclined to the 3 principal axes. So that is just exposure for you to this particular topic, and then the actual analysis starts. What happens to the material when you start loading beyond the yield point and then unloading it. So that is much more complicated aspect which is not suitable for the undergraduate course. Okay, so any questions till this point? So that is a bit heavy as I understand. So maybe in the book from Srinath, one can just simply browse through the same topic just to get ideas to what is happening. So maybe 10-15 minutes reading will give you some understanding with respect to whatever I told you. So those concepts will become more clear if you go through the book. Okay, so since we are towards the end of the course, so this we will get more heavy or more mathematically oriented topics at this particular point. Okay, so the Monday's lecture will be the last lecture where half lecture I will be covering the remaining topics, that is the principle of superposition and uniqueness theorem. So again they are more mathematically oriented, but I will try to simplify it. And the remaining half I will be covering typical end semester paper and where you can score marks. So that is like a coaching class what you had during the CET examination. So last 30 minutes would be for what questions are frequently repeated and how to score in them. So that is. Okay, so let's stop here for today and we'll meet on Monday. The second thing is next week onward we'll have the Viva for this particular course. So you must have submitted all your assignments except for the course project on the Google Classroom. Course project, the last date is 26th of this month, so that I can evaluate and before end of this month I can declare the winners of the project. And what else? Okay, the Viva will consist of 2 simple questions to begin with. So one assignments, out of 8 assignments we had, so you can prepare for one assignment thoroughly. So means you will be given choice what assignment you want me to ask questions. The questions will be simple, don't worry much, related to whatever is written in the assignment, those questions will be asked. And the second question based on the choice of my assignment, my choice of the assignment. So every person will get minimum 2 questions. If you can answer that, you will get more questions. But typically a person will not get more than 5 to 6 minutes. Considering the time limit. So if you want to excel, you have to excel in those 5 to 6 minutes like an interview. Or if you want to defend yourself, you have to defend for 5 to 7 minutes. So any other questions?